Kirumbi Engineers Skills Academy. We are available at Dar es Salaam, Tanzania, East Africa. You may contact with us through phone number +255 737 72 1910 or +255 787 85 74 85. Email us kirumbiengineering@gmail.com. Website kirumbiengineeringacademy.ac.tz. Let's continue with the limited state design. Now, in a limited state design, we shall consider the condition of the structure beyond which has no longer fulfilled the relevant design criteria. The condition here is equal to the degree of loading of the structure. Now, also, the term criteria will refer the structural integrity, the fitness for the use, the durability, and other design requirements. Also, the structure is sustainable all actions or forces likely to occur during its design life and to be remain as safe for use with appropriate level of reliability for each, the so-called, in each limited state. Now, the introduction for the limited state. The condition is working under the Woolsey's load, also under the normal load. Now here, the requirement, once we consider for the Woolsey's load, the structure should remain as safe. Now here, we have the limited state and the factor of safety. Now, under limited state, the factor of safety should be 1.35 GK and 1.5 QK. Now here, the consideration is, we have the consideration under limited state. Now, under limited state, as per Euro code, for the permanent load or dead load is 1.35 GK and 1.5 QK. It means you times the action load, or we say the live load or the imposed load, with the 1.5 under Euro code. But once you use the BS code, it is about 1.4 times the GK and 1.6 times the GK. So you can refer for the BS and you can do the comparison, and it depends on which code do you use on your design. But under limited state, for the Euro code is about 1.35 GK and 1.5 QK, and this is, you can refer for the Euro code under limited state design. So this is for the Woolsey's loading. Also, under normal loading, we say the member should not be distracted from the appearance, the durability, the performance. And this is normally we say this is a serviceability limited state, or SLL. LS. And usually we say that under the limit state, under the ultimate limit state, the factor of safety is, as I said, that 1.35 GK plus 1.5 QK, and this once you consider the Euro code, while the same value can be changed as you consider the BS. This one will be 1.4 GK plus 1.6 GK. But for the ultimate, for the serviceability limit state, this one will be, the factor will be 1. So this is 1 times GK plus 1 times QK. And the condition or the requirement should not distract under the appearance, the durability, the performance of the structures. And this is called under normal loading, and this is the normal loading consider the serviceability limit state. Now generally the three basic method for unity factor should be considered in order to achieve safe and workability of the structures. Now the three considerations are the permissible stress method, and the load factor method, and the so-called the limit state method. So under different considerations, the consideration now will be as follows. Now consider the first method. We consider the permissible stress. Now if you consider in terms of material stress, the factor of safety will be limitation under the following. It is simple, but it is not inconsistent, and basically it is based on elastic stress distribution and not applicable. So also we say that is not suitable when the deformation is not proportional. So it means under, for example, in the slender of the columns, now it is not suitable for it to consider. Also unsuitable when dealing with overturning of the forces or the actions. So this one, once you consider under permissible stress method, the factor of safety, you consider the material strength. Now always we say this no longer used in design once you consider on designing. The second one is the load factor method. Now the factor of safety here, the factor of safety, once you consider the permissible stress method, is you take the material strength over the factor of safety, and this you say no longer use. But once you consider for the loading factor, the factor of safety, once you consider for the load, it is you take the working load times the factor of safety. Now the limitation is the ultimate strength of the material must be calculated. Also it does not apply when the factor of safety of the material. The material stress cannot be directly accountable for the variable materials. If the material is variable from one section to another, it is not be applicable. Also cannot be used once you calculate the deflection or cracking. So also in general we say no longer in use once you consider for the design. But the third one is the limit state method. Now under the limit state method, you take the working load, you times the partial factor of safety. Now here the material strength divided by the partial factor of safety, it is considered a boss. Now the limitation of this one is applicable, applied the partial safety factor, both the loading and the material strength is applicable or the same or under simultaneous. Also, it is more flexible. Now this one is the considerable adaptable, now on consideration for the design. Now so under designing we consider the limit state method and not the load factor or the mass permissible stress factor. It means in design you take the working load times the partial factor of safety. Now the limit state. Now the purpose for the design is to achieve the acceptable probabilities that the structure will not become unfit for the intended use. Now the limit state not reached. It means the consideration once you want to design the limit state, the state which is considered as the maximum should not be reached. Otherwise, once it is reached, the structure should be collapsed or it will come to not used for the intended use. So that's why we say the limit state, under limit state we take the maximum achieved probability for the structure for the intended use. It means we assume that the intended use, the limit state should not be reached. Now the two types of the limit state. Now, under considering the limit state, now the two considerations for the limit state. The first one is the ultimate limit state. The second one is the serviceability limit state. Now, what the difference or what the consideration under ultimate and under serviceabilities? Once you consider the ultimate, it means the requirement of the structure should withstand to load safety against the collapse. Also, the possibilities of buckling, overturning, accidentally, or damaged. Now these are under ultimate, should be all considered under ultimate. No collapse, no accidental, and no overturning, and no buckling. And these are, we say, ultimate limit state. If you consider the ultimate limit state, these should be all safe: the collapse situation, the accidental, overturning, and buckling. But once you consider the design under serviceabilities, now the requirement of the serviceability, the deflection should be safe, the cracking, the durability, the accessibility, vibration of the structure, the fatigue, the fire resistance. All these circumstances, even the earthquake, should be considered to be safe. Now this condition, we say the serviceability of the structures. Once you consider the structure is safe as mainly the deflection, the cracking, the durability, this you say the serviceability of the structure is designed safe. But once you consider under collapse, accidentally, overturning, or buckling, we say the structure is safe under ultimate state. So more consideration for the vibration, the fatigue, the fire resistance, and even the earthquake. And this is, as we say, and now this is consideration for the serviceability limit state. Now generally we have two conditions for the design. The first one, we say this is the ultimate limit state. The second one is the serviceability limit state. And ultimate limit state, the consideration as I said here, which is the collapse one, the buckling, the overturning, the accidental. And under ultimate limit state, the consideration is, as here mentioned, the deflection, the cracking, durability, vibration, the fatigue, the fire resistance, even the earthquake. Now these are the two considerations for the limit state, in which you consider the ultimate and the serviceability limit state. Now, the characteristics of the material. The characteristic strength of the material, we say the material strength is unlikely to be lower than the required value. Now, the assumption for the strength of the material is normally under distribution curve. Now, the distribution curve is as described below here. Now, this is the curve for the characteristic strength, in which the characteristic strength is considered as the mean minus the 1.64 times the standard deviation. Now, always it lies between less 5% and not exceeding 95%. So it means the 5% is lower and higher. So the value is between 5% to 95%. And these are, here is the mean stress, and the curve describe the value between lower 5% and not exceeding 95%. It is between the value here. Now, empirically, the value can be obtained of the difference classes of the concrete. Once you consider grade 20 can have your value as calculated from the formula mentioned here. So you can pass through for the difference values, and you can have your values obtained from the tables, in which you can have the characteristic strength of the material under the deformation of the concrete. And this is always obtained from the so-called table 3.1, in which you can pass through and you can have your strength depend on the strength and the deformation of the concrete as empirically calculated. Now, the characteristic actions or the characteristic force. The characteristic force or the characteristic actions, we say the force of the structure can be designed or to be designed. Now, the characteristic actions is depend on the following. The first, the boundary, the equation, and the applications. Now, the maximum values is just the summation, the mean force times or plus 1.64 times the standard deviation. This is the maximum. But the minimum, it is the opposite. It means here you have the subtraction. The mean force minus 1.64 times the standard deviation. Now this one, we say that the maximum one from this equation is most usually applicable, but the minimum one in continuous members. Now also it is the function between 5% to 95%. Now the from the mean value here the minimum and here the maximum. It means here you add, here you subtract. So it is this value. It means less 5%, not exceeding 5% from 95. It means the value is 90%, in which if you divide it is 45% from each side. So the maximum and the minimum, it depends on the number of cases and the number of actions. For the curve is like it is be for the characteristic strength, the same properties as you have from the characteristic strength. Now the partial factor of safety. Now the cause of the errors and inaccurate. Now the design of assumptions and inaccurate calculations, this is scattered by the partial factor of safety. So we take the partial factor of safety in order to cut off all the errors or inaccurate, or the assumptions can be not correct, or in inaccuracy of the calculation can be not correct. So in order to cut off the structure to remain safe, you consider the partial factor of safety. So the possibilities of unusual increase of the magnitude of the actions. You can assume the use is residential, while in use of the structure can be used as the storage. So the magnitude can increase because your first assumptions as a designer is not used for the long time of the structure. So in order to cut off the unusual or unpredicted, so use the factor of safety in order to cut off the unforeseen. For all the unforeseen can be cut off. Even in construction, you can have a minor mistake on the construction time. So these are cut off by the partial factor of safety. Otherwise, the structure cannot be have permanent. Otherwise, we say that in order to cut off the unforeseen, you use the partial factor of safety. Now, the partial factor of safety, it is said the tolerance applied to the material, strength, and action. So generally, once you use for the factor of safety, in order to have any tolerance applied for the material, strength, even the action or the force during the use of the intended use of the structure. So generally, we say that if we consider in terms of material, the design strength FD, it is the Cartaxes strength over the main partial factor of safety, and this is you consider in terms of material. It means if you want to find the design strength of the material, if we take the rebound hammer test, say, so the Cartaxes strength you get, you divide by the partial factor of safety, so you have the design strength estimated. But in terms of force or in terms of actions, the design force or the design strength or the design load, it is the Cartaxes strength times the partial factor of safety. That's why we say let's say 1.4 times GK or 1.6 times QK. So that one, in terms of force, you take in terms of times. In terms of material, it is the ratio or dividing. So that's the difference between. So take note, once you consider in terms of material, the design strength is the Cartaxes strength divided by the partial factor of safety. But once you consider in terms of force or actions, the design action, it is Cartaxes strength times the partial safety factor. Otherwise, you can do wrong. So you can pass through the compressive strength of the design, compressive strength, as we said that in terms of material, you take the Cartaxes strength divide times this value here. But if we consider the concrete, the value of the partial factor as per this clause is 1.5. So this one you can put the lower value here. The lower value here, it is about 1.5 there. And this one is the grade strength of the assumed concrete. But if we consider for the steel, the tensile steel, the same applied, you divide because that is the material. But the value here is about 1 as recommended, and it is valid. It is about 0.8 to 1. So this is the coefficient. So from the table, under percent, the value for the concrete is 1.15, but the steel is 1.1. I mean, for the concrete is 1.5, for the steel is 1.15. Now this is for the pre-stressed, and this is for the reinforced. And accidentally, this is 1.2, and this is 1, and this is 1. So it depends on the condition and how you consider for your design. So use it for the patient, and this we say this generally for the normal use. But the transient is the temporary uses, say during the execution or the repair. But the accidentally, it means this is exceptional conditions, say during the fire or explosion or the impact load or the consequence of the localized failures. And this is, you say, under accidental conditions. So on consideration for the partial factor of safety, you can use under which conditions, whether it's a normal use or patient or the transient or accidental, and the condition is as we said here. Now once you pass through under different condition, condition A, we consider the condition A is under checking the static equilibrium of the building, and this is depend on whether it is unfavorable or favorable. For all the permanent load or dead load and the leading variable load or imposed load or live load, so it depends on the leading action or accompanied actions. So both can be considered whether it is favorable or unfavorable. For the values for the unfavorable under equilibriums, it is this one, and the favorable this one. Always the favorable, the value is lower than unfavorable. So but for the imposed load or the live load, the value is constant, if you see for the table here. But for the favorable or the live load, value for favorable is always 0. Now the conditions is 3 conditions. The first condition, you check whether you check only for the stability of the building. But the second condition, you check the design of the structure member excluding the geotechnical. Now here we say the design of the member of the structural member. Now the consideration here is under the designing of the structural member excluding the geotechnical actions. So under this circumstance, the partial safety factor is 1.35 under unfavorable and 1 for the favorable. Look, here is always once we consider for the Euro code is 1.35, but under BS is about 1.4. So the same applied is 1.5 under Euro code, under BS is 1.6. So this is the always most usable conditions for the design. Now this is for unfavorable under permanent load or dead load, and this is unfavorable under live load. Always for the favorable live load is 0, and the favorable imposed load or permanent load as per Euro code is 1. So this is the most applicable in designing. And another third conditions is, as we say, it is alternative between A and B. So the factor is this here. And note that for the live load, either accompanied action or leading action, the value is the same. But all the cases under the serviceability limit state, the value for all cases is 1. Whether it is permanent load or permanent action, means the permanent dead load or live load, the value is considered is 1. Now when passes through the action and the examples. Once you consider the permanent load is likely self-weight or the finish of the structures. this load called permanent load, or in BS we say dead load or GK. The variable load, the example of variable load is imposed load arising from the traffic of the peoples, or the wind load, or the snow load, or the likely value like that one. And this one in BS we say the live load, but in Eurocode we call the variable load. Now the leading variable action, this is like the structure such as the imposed clouded load, like the translate load or dynamic load. That's we call the clouded load, like any dynamic load or movable load. Now the accompanied variable load is the secondary action, such as the effect of wind loading. These are considered as accompanied variable load, or GK or GKI. This is GK1. Now the partial factor of safety. The partial factor of safety for the ultimate limit state with its condition of load. As we said, it depends on the type. If whether it is type 1, or once you want to check only for the static of the structure or the equilibrium of the structure, the value for unfavorable is 1.1 and the favorable is lower, 0.9. But for the once you consider for once you consider for the live load or action load, the value is unfavorable 1.5, but for the favorable is 0. For the boss leading value, it is 1.5, and the accompanied value is 1.5, but for the favorable is 0. The alternative here is only for the permanent load. For these three conditions, the permanent load or the dead load, its value is variable, it is changing. So you can pass through here for this table. You can look, it depends on the condition. If condition B, the value is 1.35, here is 1. If condition A 1.1, here is 0.9. If condition C, here is 1.3, here is 1.15. So look on the condition and take the appropriate value in order to design your structure. And you said that all the values should be considered for the serviceability cases. Now, as we say, once you consider the partial safety factor, we say the favorable and the unfavorable. Now, these terms refer as the following. Once we say the condition for the favorable, it means the effect of that value of that load is always decreasing to the member or to the structures. It means it is considered it is favorable once the load it decreasing its value for the structures, but the load is considered to be unfavorable once it increase. Once it is loaded, it is increasing the action of the structure. It means the action of the load is increasing. It reduces the stability. So once you consider it is unfavorable, it means the value it is increasing the loading action to the structure. But is considered favorable once it is decreasing the loading action for the structure. And there is the difference between the favorable or unfavorable. And that one affected the so-called the partial factor of safety on consideration for the design, whether it is favorable or unfavorable. For example, for the ultimate limit state, say determine the cross-section area for the steel capable to support the given load. Now you are given the Cartaxes action or the Cartaxes load. For the permanent or dead load 3, and the live load is 2. the nature of loaded is this one as seen. Now the steel cable is this one, the lift box, the GK, which is this one, and the live load, which is this one. Now consider the yielding strength of the steel is this value. Other factor of safety, as we said, for the GK and QK, it depends for the Euro code. Once it is in BS, you can use 1.4 and 1.6. Now the solution. The design load is always, once you consider for the action, it means you take the value times the partial safety factor. Now the dead load is 1.35 times the dead load, and the imposed load or the action load is 1.5 times the load. So the summation, you get the design load. Now once you consider the stress is always the Cartaxes strength over the partial safety factor of the material. So for the steel, you are given the Cartaxes strength is about 500 over the partial safety factor. So you have your stress like that one, Newton per meter per millimeter square. Now after having that one, now you say now once you have your stress, it means the cross-section area is the design load over the stress. So the design load, as you calculated here, times by 1000 in order to have your in terms of newtons, you divide by this value, you have your cross-section area of the lobe or of the steel lobe is about 16 millimeter, 16.2 millimeter square, and that is how you can calculate your value of the cross-section area for the given data and for the given stress of the steel lobe. So the final answer will be in terms of area, and this is this one value. Now example of overturning. A beam is supported by the foundation A and B, and the load is as given. The own self weight is about this one UDL, and the variable load or the imposed load, which is concentrated load, is about 170 kilonewton. Now determine the weight of the foundation at A to resist the uplifting. Now the condition given is applying the safety factor about 2 for the working load, and secondly by using the limit factor, given the partial safety factor is about this in terms of GK and QK. Now once you consider this one, and then you can consider for once you investigate this effect, once you increase by 77% for the variable load or the imposed load. Now the given member, it is loaded like this one. The value of length is this one, point B is here, point A is here, the uniform load is this one, and the imposed load at point C is this one. Now the solution. The solution is as follows. Once the first way is consider the factor of safety is 2. Now from the equations of equilibriums, once you take moment at point B, now the reaction A times its length, you get the moment. The clockwise moment should be equal to anti-clockwise moment. So this load times its perpendicular distance, you get the anti-clockwise moment here. Also the uniform distributed load, a half of it times the distance from support B, you get the moment for the uniform distributed load. The uniform distributed load is this load here times this plus this one, you get this plus this one, you get 8 meter. So you times by 8, a half of the 8 meter is 4 meter. It means from a half here. Now the 4 meter, because here is already carried 2 meter, it means from here to B is 2 meter. So times the perpendicular distance 2 meter. Now the summation of the clockwise and anti-clockwise is equal to 0 at equilibriums. Now at equilibriums you can solve the value of A, and you get the value of a reaction at A is about 3.33 kilonewton. So this will be the upward reaction at point A. Now solving the equilibriums of the moment, you can have your value for A. Website Kivumbi Engineering Academy.ac.tz.